Our goal in this lecture is to explore the theoretical foundations of diagonalizations in greater detail. We'll begin with the following theorem. Let T from Fn to Fn be a linear operator with matrix A. Then A is diagonalizable if there exists a basis of Fn consisting of eigenvectors of T. And we recall that the matrix A is diagonalizable if and only if there exists an invertible matrix C and a diagonal matrix D such that A is equal to C times D times C inverse. We have already proved half of this theorem. So we proved that if there is a basis of eigenvectors, then A is diagonalizable. Well, let us sketch this proof. So suppose B being V1 through Vn be a basis of eigenvectors of T. So this means that T applied to Vj is lambda j times Vj, where lambda j's are eigenvalues in F. Then we construct C by placing basis vectors V1 through Vn as columns. Now, this matrix is the change of basis matrix from basis B to the standard basis. Since Vj's are eigenvectors, so the matrix of T in basis B is going to be diagonal. And so it will have eigenvalues on the diagonal. And then we have the change of basis formula that the matrix of T in the standard basis can be written as a product of three matrices. So we have the matrix of T in basis B, then we have change of basis matrix from standard basis to B, and the change of basis matrix from B to E. And then, so the matrix on the left is the matrix A. Then the left factor is C times the T in basis B is diagonal. And the change of basis from standard to basis B is the inverse of C. And we obtain that matrix A is diagonalizable. Let us now prove the converse. So we assume that A is diagonalizable and let us prove that there exists a basis of eigenvectors of T. Since A is diagonalizable, then we have that A is equal to C times D times C inverse. let V1 through Vn be columns of C. Since C is invertible, we know that its columns form a basis of Fn. So we need to show that these are eigenvectors of A. We have that C inverse times C is equal to identity matrix. Now, this tells us that C inverse times the jth column of C is equal to jth column of identity matrix, which is EJ. So this is a column of zeros with 1 in jth position. This is how the product of matrices works. So the jth column of the product is the left factor times the jth column of the right factor. Now, let us compute A times the vector Vj. So this is C times D times C inverse times Vj. And Vj is the jth column of matrix C. So then, by what we wrote here, C inverse times Vj is equal to Ej. So we have C times D times Ej. But D is the diagonal matrix, and so when we multiply Ej by the diagonal matrix, so it's getting multiplied by the corresponding entry on the diagonal. So this is C times lambda j Ej. Or this is equal to lambda j times C times Ej. But what is C multiplied by the column vector Ej? So this is going to be lambda j times the jth column of C. And thus the result is lambda j times Vj. And this shows that Vj is an eigenvector of A with eigenvalue lambda j. And now we conclude that we have constructed a basis of Fn that consists of eigenvectors of matrix A, or equivalently eigenvectors of transformation T. What we want to do today is to prove a slightly different version of the criteria for diagonalization. So we're going to prove the following theorem. An operator T from Fn to Fn is diagonalizable if and only if the sum of dimensions of eigenspaces of T is equal to n, to the dimension of the vector space. What is our computational procedure for diagonalization of matrices? First, we compute the eigenvalues of the matrix as roots of the characteristic polynomial. And then for each eigenvalue, we compute the basis of the corresponding eigenspace. And then we want to put bases of eigenspaces all together to form a basis of the whole space consisting of eigenvectors of our operator. However, there is a potential problem. So it is a priori possible when we take linearly independent sets and put them together, we could potentially get a linearly dependent set of vectors. And we need to form a basis. What we're going to prove today is that if we join together bases of eigenspaces, then the resulting set will automatically be linearly independent And if it has the right number of vectors, it will be the basis of Fn. Before we can prove this theorem, we need to establish a couple of technical results. Lemma. Suppose we have two sets of vectors u1, uk, and w1 through wk in a vector space V. Assume that we can express w vectors in terms of u vectors. w1 is equal to a11 u1 plus a1k uk. w2 is a21 u1 plus a2k uk, and so on. wk is equal to ak1 u1 plus akk uk. Suppose matrix A formed by these coefficients is invertible, and let B be the inverse matrix. So B is made up with coefficients Bij. Then we claim that we can express u vectors in terms of w vectors. For all I from 1 to k, we have ui is the sum s goes from 1 to k, bis, ws. So we have a symmetric relation between u vectors and w vectors. So we can express u vectors in terms of w vectors in exactly the same way, only using the coefficients of the matrix B, which is the inverse of this matrix A. Let us introduce a notation that we will be using throughout this course. So this is called Kronecker delta. So delta ij is defined as ij entry of the identity matrix. So delta ij is equal to 1 if I is equal to j, and it's equal to 0 if I is different from j. So diagonal entries of identity matrix are equal to 1, and off-diagonal entries of identity matrix are equal to 0. So this function on two indices, delta ij, is called Kronecker delta. Now, these formulas here say that ws is equal to the sum j goes from 1 to k, a sj times uj. Let us evaluate the right-hand side of this equality. So here we have the sum s goes from 1 to k, bis times ws. But here we have an expression for ws. So we get the sum j goes from 1 to k, and then we have the sum s goes from 1 to k. We have bis times a sj times uj. But what is this sum here? So this sum is nothing else as the ij entry of the product b times a. But that's an identity matrix because b is the inverse of a. And then we get the sum j goes from 1 to k. Now the ij entry of the identity matrix is the Kronecker delta, delta ij, times uj. But then in the sum, the only coefficient which is non-zero is when j is equal to I. And then all other terms, when j is not equal to I, all these terms will become 0. And then what we get is 1 times ui, or just ui. And in this way, we have derived this formula here, that ui's is expressed as this linear combination of ws's. And that's exactly this kind of a relation. And I here was an arbitrary index from 1 to k. So this lemma tells us that if we can express w's in terms of u's with a coefficient matrix which is invertible, then we can express u's in terms of w's in the same way using the inverse matrix. Next, we prove the following proposition on linear independence. Let t from fn to fn be a linear operator and suppose t of ui is equal to lambda I times ui, or I goes from 1 to k, with lambda I different from lambda j for I different than j. If we have that u1 plus u2 plus uk is equal to 0, then all of these vectors are equal to 0. Now, as a remark, we can note that we could have used the slightly different notations. So if we suppose that ui is ci times vi, with vi's being non-zero, then we could have stated this in the following way, that if c1 v1 plus ck vk is equal to 0, then this implies that c1, c2, and ck is equal to 0. So this is an equivalent statement of this proposition, and this statement is the statement of linear independence in its pure form. But for us here, it is technically more convenient to state this proposition in this way. So let us give the proof of this proposition. What we have is we have that 0 is equal to the sum u1 plus u2 plus uk. Now let us apply t to both sides. We have t of 0 is equal to t of u1 plus t of u2 plus t of uk. But t of 0 is equal to 0, and t of u1 is equal to lambda 1 times u1. T of u2 is lambda 2 times u2. And t of uk is lambda k times uk. Now let us repeat this. So apply t again. So we'll get 0 is equal to lambda 1 t of u1 plus lambda k t of uk. And what we're going to get is that 0 vector is equal to, now we have lambda 1 squared times u1 plus lambda 2 squared times u2 plus lambda k squared times uk. And now we repeat this k minus 1 times until we get the following equation. 0 is equal to lambda 1 to the k minus 1 u1 plus lambda 2 to the k minus 1 u2 plus lambda k to the k minus 1 uk. Now we have two sets of vectors. So we have u1 through uk, and we also have vectors that appear in the left-hand side. So w1, which is a 0 vector, w2, which is a 0 vector, and wk is a 0 vector. And here we expressed wj's as linear combinations of ui's. And what is the matrix that connects these two sets of vectors? Well, the first row of coefficients is all ones. The second row is lambda 1, lambda 2, lambda k. The third row is lambda 1 squared up to lambda k squared. And the last row is lambda 1 to the k minus 1 up to lambda k to the k minus 1. And we see that this is the van der Monde matrix. And since lambda i's are all distinct, lambda I here is different from lambda j, our formula for the van der Monde determinant tells us that determinant of A is not equal to 0. And hence, A is invertible. And then, for all I from 1 to k, we can express ui in terms of wj. So this is the sum s goes from 1 to k by our lemma. So this will be bis, where b is the inverse matrix of this matrix A, which exists, times ws. But all ws vectors are all equal to 0. So hence, the result is equal to 0. And we get the claim that all vectors ui's are equal to 0 vector. Next, we're going to prove a proposition that says that when we join bases of eigenspaces, the resulting large set is going to be still linearly independent. Proposition. Let lambda 1 through lambda k be eigenvalues of the operator t. Let mj be the dimension of the eigenspace corresponding to lambda j, and let v1 through vm1 be a basis of lambda 1 eigenspace. vm1 plus 1 up to vm1 plus m2 be basis of lambda 2 eigenspace. Dot dot dot, and the following set vm1 plus m2 plus mk minus 1 plus 1 all the way up to vm1 plus m2 plus mk, so be a basis of lambda k eigenspace. Then the union, so if we put all these sets together, so we have v1 dot 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 vm1 vm1 plus 1 dot 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 vm1 plus m2 dot 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 up to vm1 plus m2 plus mk. this set is linearly independent. So here we take bases of all eigenspaces, put them together, and we claim that this large union of the bases of eigenspaces will still be linearly independent. Let's give a proof. Consider a linear combination of these vectors. So C1 V1 plus CM1 VM1 plus CM1 plus 1 VM1 plus 1 plus CM1 plus M2 VM1 plus M2 plus dot 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 all these vectors, and we equate this to a zero vector. Next, we set this group, this sum, to be U1, the next sum to be U2, and so on, and the last sum to be UK. Then what do we have? So we have U1 plus U2 plus UK is equal to zero vector. But U1 is a linear combination of eigenvectors corresponding to lambda 1. So this means that T of U1 is equal to lambda 1 U1. And for all of these vectors, we have this property. So UK will be a linear combination of eigenvectors that correspond to lambda k. So T of UK will be lambda k UK. Then we are precisely in the situation of the previous lemma. So since we have the sum of these vectors is equal to a zero vector, and each of these vectors satisfy T of ui is equal to lambda I ui, and all eigenvalues here are distinct, we conclude that each group of these vectors is equal to zero. So each vector ui is a zero vector. Now let us analyze. So if u1 is equal to a zero vector, what does it mean? So this means that this first group of vectors is equal to the zero vector. We get c1 v1 plus cm1 vm1 is equal to a zero vector. However, so this set of vectors v1 vm1 is a basis of lambda 1 eigenspace. And since it's a basis, this set is linearly independent. And from here, we conclude that all these coefficients are equal to 0. So C1, C2, up to Cm1, this is equal to 0. Applying a similar argument, we get that coefficients in all groups are 0. So this means that all coefficients in this big linear combination are all 0 coefficients. And this gives us the claim of our proposition. So we proved that when we join the bases of eigenspaces, the resulting big set is going to be linearly independent. As a corollary, we get that the sum of dimensions of eigenspaces of operator T from Fn to Fn does not exceed n. So we claim that the sum of dimensions of eigenspaces cannot be greater than n, because if we join the bases of these eigenspaces together, where we'll obtain a set which is linearly independent. And the size of this set cannot exceed the dimension of the space, because there are no linearly independent sets in Fn with the number of vectors greater than n. And since the size of the union is equal to the sum of dimension of eigenspaces, we obtain the claim of this corollary. Now we can prove the main theorem of this lecture, that operator T from Fn to Fn is diagonalizable if and only if the sum of dimensions of eigenspaces of T is equal to n. Let's give a proof. So here this is an if and only if statement, so we need to prove two parts. Now suppose the sum of dimensions of eigenspaces is equal to n. Let us show that this operator is diagonalizable. Let lambda 1 through lambda k be eigenvalues, and let b1 through bk be bases of eigenspaces. Form a set B as a union of all these bases. By our previous proposition, the set B is linearly independent. And since the sum of dimensions is equal to n, we have that the size of this set is equal to n. So hence, B is a basis of Fn consisting of eigenvectors of T. And by our previous theorem, if we have a basis of the space consisting of eigenvectors, we have that this operator is diagonalizable. Now let us prove the converse. So suppose T is diagonalizable. So this tells us that there exists a basis of Fn consisting of eigenvectors of T. And this tells us that the sum of dimensions of eigenspaces is greater or equal to n, because we have enough eigenvectors to form the basis of the whole space. But by corollary, we know that the sum of dimensions of eigenspaces is less or equal to n, always. And from here, we conclude that if operator is diagonalizable, then the sum of dimensions of eigenspaces is equal exactly to n. And this completes the proof of this theorem. Now let us look at the following example. Suppose we have the following matrix A: 3, 1, 0, 0, 0, 3, 1, 0, 0, 0, 3, 0, 0, 0, 0, 4. Since this matrix is upper triangular, so we can easily see the determinant of A minus lambda I is equal to 3 minus lambda cubed times 4 minus lambda. So from here we see that eigenvalues are lambda 1 is equal to 3 and lambda 2 is equal to 4. If we take A minus 3I, we get the matrix 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, and 0, 0, 0, 1. So we see here that the rank of this matrix is equal to 3. And by rank nullity formula, we conclude that dimension of lambda 1 equals 3 eigenspace is equal to 1. Now, if we take the second eigenvalue and consider A minus 4I, then the matrix that we obtain is minus 1, 1, 0, 0, 0, minus 1, 1, 0, 0, 0, minus 1, 0, and 0, 0, 0, 0. And again, we see that the rank of this matrix is equal to 3. And by rank nullity formula, dimension of lambda 2 equals 4 eigenspace is also equal to 1. So the sum of dimension of these eigenspaces is equal to 2, and the matrix has size 4. So our conclusion that this matrix A is not diagonalizable. Going from real to complex numbers will not help us, because going to complex numbers can only help you to factor your characteristic polynomial. But this characteristic polynomial is already factored into linear factors. So going to complex numbers will not change the situation. So this matrix is not diagonalizable neither over real numbers nor over complex numbers.